and I want to welcome you to today's webinar. The title of today's webinar is Introduction to Protection and Controls. And we're going to, in just about 1 or 2 minutes, we will get started. I think we still have quite a few people logging on, so we will get underway here in just about 1 or 2 minutes. So hopefully everyone can hear, and you should be able to see right now Roger's bio, and we will be back in just a moment. Thank you. Okay, once again, we're going to go ahead and get underway. My name is Brian Hudson. I work for ABB, and I want to welcome you to our webinar for today. This is the first in a series of webinars, and today's webinar is an introduction to protection and control. Our presenter today's name is Roger Heading from ABB. Roger graduated from Marquette University and joined Westinghouse Electric Corporation. After receiving his master's degree, he became a district engineer and eventually moved to Milwaukee, where he currently resides. And as a relay development consultant, he guides the development of relay products for North American market. Roger is an IEEE senior member and a vice chair of the IEEE Power Systems Relay Committee. Roger has authored or co-authored many papers in power systems protection. We're anticipating that this presentation will last somewhere between 60 and 90 minutes. If you have a question at any time during this presentation, I suggest that you type your question in your control panel question pane, and we will read the question on the air and respond to it. Also, I wanted to let you know that this session is being recorded. So if anybody would like to view the recording at a later date or knows someone who would like to register and view the recording at a later date, to feel free to do so, that this session will be available online in about 24 hours. And with that, I'm going to turn the presentation over to Roger.
Thanks, Brian. Welcome, everybody. Welcome to our first of many webinars we'll be holding over the next several months. As Brian said, this first webinar is called Introduction to Protection and Control. So it'll be the very, very basic seminar about some initial concepts about relaying, which will be expanded upon in future webinars that we have. What we hope to cover during this seminar are an overview and understanding of the role of protection and control in the industry. We'll define some relay classifications about types of relays that exist, talk about some common relay applications, understand some relay philosophies about protection, review some basic protection principles that are being used. Okay. And then we'll talk about some IEEE device numbers, and then finally some symbols used for protection and control, both the IEEE device numbers and symbols and the IEC symbol. As we said, if anybody has any questions along the way, please use your chat box and indicate the question, and then we'll review that and respond. First of all, we're talking about protection and control. We first need to understand what is relaying. Lots of ways we can just talk about relaying. If we look at the definitions of relaying that are in the dictionary, it comes under several different definitions. One is an act of passing something along from one person to another or one station to another. It could be a supply as a horse is arranged beforehand for successful relief. It could be a number of persons who relieve others in some work. Or, lastly, an electrically operated switch that responds to a current or voltage in one circuit to switch on or off the current or in the second circuit. Relays derived from the French word relays, which at the time meant replacement. The term relay was first applied in 1830 to a team of relief horses that were pulled horses or vans or railway cars on wooden wheels on the wooden railway between Baltimore and Ellicott Mills. The term relay was applied to the station where the work horses were changed for fresh horses to continue on the journey without any delays at all. And the Old West stagecoaches used relay stations where they changed horses before they continued on their journeys. And in 1860 and 1861, the Pony Express used the word relay when they changed riders to go from moving mail from one place to the next. So you can see we have a real rich history with relays in the nation. About the same time, electromagnetic technology was evolving. The first electromagnetic relay or invention with using electromagnetism was invented and applied for U.S. patent between 1830 and 1875. Joseph Henry had a telegraph electromagnet where he took a battery and connected a relay to it, and then connected over long distance to a receiver that could decode his opening and closing of the switch by the discharge and the second relay. Samuel Morse took the same approach and developed this repeater that was used for Morse code for years for the telegraph industry, using a keyer and transmitting this keying information over long distance to so that the other end of the line would hear the sound of the clicking, which could be decoded as a 1 or a 0 for Morse code, or a dash or space for Morse code. Recognizing the similarity between the relay horses that were used to exchange information, how to exchange riders going from place to place, and the telegraph repeaters and sounders that the telegraph industry used, these telegraph electromagnetic devices were originally called relays back in the 1870s. Hence the word relay being applied to the closing of an electromagnetic contact that we still use that word today. The first electrical relays were used over long distances, telegraph distances, to repeat incoming signals from across, and then retransmitted to the other end of the line. Just as relay horses were used to exchange riders to head on down the line to deliver the mail. In the electric power system, in the early 1880s was a very, very sparse system with very few wires, very few, and service interruptions were no big deal because it didn't really rely on electric power. They rely on it today. The wires running on the line were very thin wires from place to place, and fuses were the only means of protecting the wires. Even actually the wires themselves turn out to be fuses in many of the cases. Electromagnetic switches were operated to switch the electricity from one wire to the other one, but there was still no way to discriminate between faults at all, and we didn't really apply any of the relays as we know them today at this particular time. The first protective relays were really introduced in the 1900s, and you can see here a vintage old Westinghouse relay that took the shape of a watt-hour meter type of enclosure, because they came out before meters. Of course, we wanted a meter before we did do any protection. And then as the industry progressed, as you can see the timeline going across, we finally went to the modern FT switch type of electromechanical relays we know today. Then we evolved into, the solid-state relays, then into the microprocessor-based relays, then finally to the relays as we have them today. So we have a very rich history dealing back into the late 1800s, early 1900s in this relay technology. So the common definition for relays now is a device that responds to a measured quantity of current, voltage, heat, pressure, vibration, or some other physical quantity from one system and switches the current in another system, usually an electric circuit, for the purpose of protection and control. Protective relays are devices that are used throughout the electric power system to detect abnormal or unsafe conditions and initiate corrective action. So that we can classify relays according to IEEE C37.90, which is a standard by which relays are manufactured and tested. At this point, I'd like to give a slight plug for the Power System Relaying Committee that it's responsible for developing these standards for the electric, for relays and whatnot, that meets 3 times a year throughout the country. And you're all welcome to become and attend their meetings whenever you'd like. The next meeting happens to be in September in a couple of weeks in Minneapolis. But relays could be classified several different ways. Protective relays detect intolerable conditions and defects in apparatus. Monitoring relays monitor the conditions of what's going on in the system and don't necessarily take any action, but just they're monitoring. For closing relays that are just used as that, they will actually initiate a reclosing sequence after some protective device is operated and open up the circuit. Regulating relays maintain the voltage or current within a certain parameters based on what range you want to give it. Auxiliary relays operate after another initial relay operates to give additional functionality to the opening many contacts rather than one contact. Synchronizing relays assure the proper conditions exist between interconnections before a reclosing action is taken place, or a closing action is taking place. We can also classify relays by the type of input that they're subject to. We have relays that respond to current, voltage, power, frequency, temperature, pressure, flow, vibration, and other things. We can also classify relays by the kind of performance that they have. We have overcurrent relays, over-under voltage relays, distance relays that looks at the relationship between the voltage and the current, directional relays that look at the direction that the current is flowing, the power is flowing, inverse time, definite time overcurrent relays, ground or phase relays, high speed or low speed relays, current differential relays, phase comparison relays, directional comparison relays, many different performance characteristics, and each one has a certain suited place in use in the electric power system. We can also classify relays by their kind of operating principle, whether it be a current balance relay, which one of the first relays that was made was based on a like a little teeter-totter, where with equal current and voltage supplied on both sides of the relay, it was in the balanced condition. Then whenever a fault would happen, the current would increase, the voltage would decrease, so we would get the teeter-totter to lead more one way than the other way until we eventually operated a relay, which was the original balance stream type relay. There's percentage biased relays, multi-restraint, current differential relays, product relays, thermal relays, comparator relays, phase and magnitude comparison relays. So there's lots of different ways we can classify relays, and again, each one of them has a certain purpose in life as far as the protection engineer is concerned. We can also classify them by the technology that they were made by. Electromechanical, solid state, or static relays, or microprocessor based, which went from a digital type relays to numerical type relays. Of course, the first two, electromagnetic and solid state, were both analog type relays, which operate the analog world, and the microprocessor based operate in the digital or sample world. Protective relay is just one part of the entire system, though. A protective relay can't operate by itself. A relay is used to, it has to rely on other components to do the measurement for it. So we have to have potential transformers and current transformers, or or RTDs or something that bring that information from the high voltage system down to the relay level. The relay can't detect a 2,000 amp current by itself because it would have to be so massive. So we have current transformers that take that 2,000 amp current transformer to a 5 amp or a 1 amp level, so it can be safely applied to the relay. And we take that voltage that could be anywhere between 1 kV and 765 kV, and lower it down to a 120 volt level again to apply to the relay, so the relay can be operated with a safe level. And then, since the relay can't open up the circuit by itself, it has to rely on another piece of equipment. After it makes the decision to trip, it has to rely on a device like a circuit breaker or circuit switcher to actually do the actual circuit switching to open up the lines so that the fault current stops flowing. The next piece on the system is the DC power supply. The relay has to be powered by some means, and so we have a DC power supply that will apply the power to the relay for the relay to operate. Then that same DC power supply is also applied to the circuit breaker, so the circuit breaker can interrupt the circuit. So all these devices are all go together to make up the protection team to open up for the protection. We have a question that came up about why do we use DC? In the electric power system, the one thing that electric utilities cannot rely on is AC current because of the fault. If a fault happens, you could get the voltage to go down quite low, so you have to have an external supply like DC, direct current, to supply the power to trip the breaker and to run the relays. That's why most times we use a DC battery to do the tripping rather than using AC for tripping. Other industries like the industrial customers, some of those will use AC once in a while, but in the electric utility industry, it's always using DC to do the tripping. So if we put this protection team together, this is schematically what we're look at. We have a current We have a current transformer and a potential transformer that feed information, transform the currents and voltages to a lower level, and feed it into the relay. And then after the relay operates that information, it then closes its contact, and then its contact will then in turn go through the stationary battery to energize the trip coil on a breaker, and the breaker will trip. When the breaker trips, then the 52A contact, which is a auxiliary contact on a breaker, will open up, and then that will open up the trip circuit so that the relay can be reset again. So all these devices have to work together: the battery, the breaker, the potential transformer, the current transformer, and the relay to isolate the fault from the rest of the system. Now let's look a little bit about how we go into choosing the type of relay that we're going to use for a given application. There are certain criteria that are used for selecting relays. One is selectivity, one is reliability, one is the speed of the relay, next is the simplicity of the relay, and economics. We can make a very, very fancy relay, very expensive relay for high-speed applications, but you wouldn't necessarily want to use that or need to use that type of a relay on a distribution circuit. At the same time, if I've got an extra high voltage system I'm trying to protect, I may not want to get by with using a very, very economical overcurrent relay that's very, very slow for that application. So all these factors need to be taken into account when deciding on the relay system to use for any given application. Dependability and security have always been at each other's throat. You want to have a relay that's very, very dependable, which means it's going to operate correctly when the system has a problem. At the same time, it has to be very secure so that if it doesn't misoperate, it doesn't operate when we don't have when either a fault is outside this area of protection, or there isn't a fault at all. So you can make a case for a relay being extremely dependable yet lacking security. So this is always a kind of like another one of those balance beams that we've got to worry about. The good balance between dependability and security. If you wanted a very, very dependable system so that it would always operate every time we had a fault, then we could put two contacts in parallel to each other. So we have a main 1 and main 2, such that if either main 1 or main 2 sees a fault, then we'll be sure to operate, and so that we'll have to get our dependability up. At the same time, if you want the system to be very, very secure, you can picture that as having main 1 and main 2 in series with each other, so that both main 1 and main 2 would have to detect the fault before they would operate. So we minimize any chances of either main 1 or main 2 misoperating, causing the whole system to go down. So this is how we look at one versus the other. Another question came in. Well, question came in, do we need the same AC and DC supply for the breaker and relay? In most cases, the ideal thing ideally you would have a different DC supply for the breaker and the relay. But from the practical aspect, you really can't get by doing the because of economics. So oftentimes you'll have the same DC supply going to the breaker and the relay, but they'll be fused separately. So that if anything happens to the relay, it will open up the fuse, and the breaker DC supply will still be maintained. So that's how either by using molten case DC breakers or using fuses between on different circuits going from the DC breaker to the relay and the breaker. I hope that answers the question okay. Now we'll look at zones of protection. There's, as anything, we try to have overlaps as much as possible between different parts of the system. As you have generators, transformer buses, transmission lines, and motors and loads, we also have to have protection for each of these. And oftentimes, we don't want to have any holes in the system for protection, so we try to overlap the protections as much as possible by using current transformers located in strategic places to do this overlap. Let's look at those now. Here's a picture of a 4-station system showing some generation, some transformers, some transmission lines, some buses, and some motor loads and whatnot. Now let's look at how we can protect us with zones of protection. First, we're going to have protection on the generator generators by itself. And oftentimes, the protection for the generator also may include part of the step-up transformer in this protected zone. We next would have protection for the transfer protection. You can see now the transfer protection could actually overlap the generator protection and go all the way to the high voltage breaker on the source side or the load side of the high voltage breaker by using the CTs again. We now look at the bus protection, and now the bus protection overlaps this transfer protection by using the CTs that are on the generator side of the breaker and for the bus protection. So we include the whole bus plus the circuit breakers in the protected zone by using CTs on the opposite side of the scheme. Now we look at line protection. Your line protection overlaps the bus protection by using the CTs on the bus side of the line, so we get overlapping protection of these breakers again. And lastly, for motor protection, we overlap our breakers again in our CTs so that our motor protection and feeder protection overlaps the protection for the bus protection we have on the feeders also. So you can see that every stage of the protection, we have overlap between each of our protected zones, so there's no part of the system that has any holes where we don't have any protection involved. Now you may ask yourself, how do we get this overlapping? We do that by what CTs we use on breakers. If you have a dead tank breaker, which means that you can go up and if it touches the tank of the breaker and it'll be at zero potential, then oftentimes you'll have availability of CTs on both sides of the breaker. And we always use the CTs, most times use the CTs on the opposite side of the breaker for the protection of the zone. So you can see for the green zone, we're using the CTs, and the green zone actually goes off to the right. We use the CTs on the left side of the breaker for that zone. Then for the red zone, we use the CTs on the right side of the breaker for the protected zone that's going to the left. Right. So that's where we get the overlap between the two sets of CTs around the breaker. In the case of a live tank breaker, which is used quite often on systems above 138 kV, then you get a problem because you don't necessarily have CTs on both sides of the breaker any longer. These are the cases where you can buy a CT that has many cores on it. Or on one core, you'll have several CTs on the same core, and you need to know the exact placement of these CTs on the core, and you could do your overlap based on the location of those CTs on that one CT core, as seen in this picture, where we're overlapping. We have a small overlapping region, but again, we're having some overlap between the two zones on this live tank breaker. A question came up again. Oh, yeah, a question came up back in our slide about our redundancy before, saying that if we for getting the maximum amount of redundancy, let's go back to that slide real quick, which was right here. Well, we have a main 1 and main 2. If this would be a way to get the maximum amount of dependability, or having both in parallel, and putting them in series would give you the maximum amount of security. But that doesn't mean you have to have 4 relays to do this scheme. This is just illustrating what the term means by security and dependability. Most times people use two sets of relays on high voltage systems to gain the dependability that they want. In some cases where they've got a very, very secure system, not secure system, but a very, very important system, like on a 500 kV system, some customers have used 3 relays all looking on the line and using a 2 out of 3 voltage scheme, so 2 of those relays would have to see the fault before you would actually do the tripping. So there's several ways people have invoked this security and dependability over the years. And that's the question came up. And could you clarify the terms dead tank and live tank breaker? Yes, a dead tank breaker is one that you usually see that has where the tank of the breaker is at ground potential, and the current transformers are typically located on the bushings going up to the line. For the live tank breaker, you'll see a long bushing column, and the head of the breaker where the interrupter is actually located at line potential above the insulator. So that's the difference between the two of them. And that actually that tank on the live tank breaker is at line potential, so you can't touch it when it's energized. Hope that answers okay. Okay, now let's look at some basic protection principles. That are used. There's a definite time over current relay, inverse time over current relay, directional, distance, differential, phase comparison, and directional comparison. Those are the ones we'll go through now. Definite time relay, here's we have a radio power system. We have a fault on the system that's indicated by this little lightning bolt type thing. We have a relay with a current transformer, and this little box is our relay. And then we have the relay, the fault current goes from the source through the relay, through the CT, out to feed the fault. We can have a fault detector that looks at above a certain current, which we see on our time versus current curve here Above a certain pickup current that we assign as IPU, the relay will operate. And that's what we see for this definite time. We set a pickup level of current. We also set a time before the relay operates, and this time could be anywhere from instantaneous all the way to several cycles or seconds before it operates. And then, so when we reach this magnitude of current and the timer times out, then the relay operates. It's a definite time over current relay. Instantaneous time over current relay follows a similar principle where we set a pickup level for the relay so that above a certain current flowing, this IR current flowing, we will assign a pickup level to that, and anything above that level, the relay will operate. But instead of having just one operating time we have a inverse curve so that the higher the current goes, the lower the operating time. The time is increasing on this y-axis, so as the current increases out on this x-axis, the amount of operating time it takes to operate that relay decreases. So if we have a current that's a small amount of current that's way over here, it takes this much time to operate the relay. If the current gets higher, it takes this much time. If the current gets very high, it takes this much time, much less. And if you're used to the terms extremely inverse, very inverse, this is where that terminology comes from. It's the shape of this curve defines whether it's inverse, very inverse, or whatever the curve you're going to be using. A question came up again. Is the definite time same as the 50 function and inverse same as 51 function? Well, a definite 50 function defines an instantaneous overcurrent relay with no intentional delay, whereas a 51 function is a time overcurrent function. So in reality, a definite time relay that has some delay in it would be a 51 function relay, which means it's a relay with some time delay associated with it. Whereas an instantaneous relay, a device 50, would have no delay at all, operating in very short time. Next comment, if we had a radio system with a couple different buses on this radio system, we can have a couple relays on this, and the object of protection is to have the relay that's closest to the fault operate for the fault before another relay operates for the fault. So for a fault that we see in our picture, where again the relay at B we want to operate before the relay at A. That's because it's a radio system. We'd want all the customers between A and B to still be fed and load intact, even though we cleared a fault for way down the line at B. So only the customers from B on out on the system would be affected by the fault, would have their service interrupted, or it still would be between A and B. So in order to do that, we would first take the relay at B, put the relay at B, and construct and set the inverse curve that you see here for the relay at B and time current curve below that you see here. And assign a pickup level to that relay. And then for the curve for B, we can take the same kind of a shape of a curve and put it on a larger time dial, which means we have more of a delay between the operation of at B than A for the same fault current, so they would coordinate together, so that the relay at A would trip after the relay at B trips for the same fault. So you can see the distance between, for the same current level that we have here, the relay at B would operate this fast, but the relay A would operate much slower for that same fault. That's how we coordinate two relays together. We also have different operating regions for the relays also. A 27 relay is a voltage relay. 27 is specifically the under voltage relay, and a 59 relay is the over voltage relay. So if we have a certain set point, say like on a 120 volt secondary, we pick 110 volts for the set point. Anything less than 110 volts on that system would operate for the 27 function. Anything greater than 110 volts would operate for the operating reason for the overvoltage function. Typically, there's some bandwidth between the two of them. We don't set them at the same level, but that's the definitions of the overvoltage and undervoltage relays. The next concept would be a differential relay. This happens to be a voltage balance differential relay where we compare the voltage on two sides of an object, and if the voltages are the same, we get no voltage difference, and the relay wouldn't operate. But as soon as we get a voltage difference between one side and the other side, and it exceeds a certain amount, then the relay operates. This is called a voltage balance or voltage differential relay. The next concept is called directional relaying. In our previous slide we had before for inverse time over current, we assumed this is a radio system, so all the fault current was fed from one source over on the far left-hand side and fed out on the system to the fault. But imagine we have another source over here on the right-hand side that was also feeding the fault. Now our coordination between these two relays would get much harder because the relays themselves are non-directional. The overcurrent relays are non-directional. Do you have a question come up?
I don't know.
Okay, a question came up. What is the time delay difference required for the two relays in operation? On talking about our coordination between these two relays, and that typically is a function of the level on the system. Is this a distribution system? Is this a transmission system? The difference in operating time between the two relays would be called the coordinating time interval. On the distribution system, this coordinating time interval is normally in the area of seconds, like 15 seconds or so. On the transmission system, this coordinating time interval is in the matter of cycles, like 15 or 30 cycles. So it depends on where you are in the system, depends on what that coordinating time interval would be. Where are we at now? Here. So we're back to so in order to get our relay to be directional, we have to use a reference point and we have to use an operating point. And we look at the angle between the reference point and the operating point to determine whether or not this is going to be a forward direction or a reverse direction. Going back to our electromechanical terms again, if the operating point is lagging the reference point by so many degrees, we can say that's a contact closing torque, as you would have like on a electromechanical relay. And if our reference point is lagging our operate by a certain point, that would be a contact opening torque. So by setting up the relationship between this reference point and the operating point, by degree-wise, we can have a forward relay or a reverse reaching relay, depending on how we set that angle between those two up. So we can have in this way we can apply a overcurrent relay on a loop system where we have sources on both ends and make it only respond to currents flowing in one direction and not the other direction.
Hello. Hi, right.
Somebody should mute their phone. Okay, here we have a directional relay for showing you a typical ways we do polarization. For multi-phase relays for phase faults, the operating current would just be the phase current, either IA, IB, or IC, and the polarization quantity is voltage polarization, and we use quadrature voltage for polarization, which means for the IA current we use a VBC voltage, or the IB current we use VCA voltage, or for the C phase current we use the AB voltage in order for our polarization quantity. And the angle between these two will determine whether or not it really operates or not for a forward fault. Similarly, for ground faults, we could either use zero sequence current, we use, for the operate current, we use 3I0 current, and for the polarization quantity, we use 3V0 current.
And you have a good day?
Sometimes we use we could also use negative sequence for operate quantity and 3V2 for the polarizing quantity. So we can use different combinations of different types of currents and voltages for the operates and operate quantities in order to get this characteristic the way we want it for our directional relay. Next in line of expense would be the distance relay. A distance relay just measures the current and voltage at a given point on the line to mimic what the voltage drop would be to a fault some part on the system. So we have a relay setting called ZR, which is the reach the relay would be set out in the system, and then we measure the voltage at the relay and the current at the relay, and do a mathematical function of V over I to determine what the current, if the impedance is within the reach of the relay or it's beyond the reach of the relay. Which is the basic distance relay. Now we have to take into account the source impedance also, but it's done in the equations for the operation of the relay. We use basic Kirchhoff's law to determine the voltage drop on the system between the source and the point of the fault. And we actually use a phase comparator and a phase comparator to do that, look at the angle between the two in order to determine if the fault is within inch reach or not. Here we have a quantity of S1 and S2, which is our phase comparator. And if S1 leads S2 by so many degrees, then we get a 1, and if they don't, we get a 0. In this case, for a fault, we can say S1 is equal to the current at the relay times the reach of the relay minus VR, and then our S2 comparator could be VR. So and then we look at the relationship between the angles between S2 and S1, and when for S2 is stationary, and you can see S1 will swing around and upshoot. When S1 is down in this region, it's a restraint, so it's not a forward fault. Unless the S2 is in this gray region, it's operating quantity and then it's a forward fault. Using that, you can construct a Mohs circle, which is the operating characteristic for this impedance relay. Now, impedance relay is different than the overcurrent relay in that it has a set reach associated with it, which means if I set this for 80% of the line between G and H is one line section here, and we typically set the relay for about 80% of that, so ZR is 80% of the ZGH, so to speak. And then this is how far the relay will reach. And there's also a maximum torque angle or operate angle associated with this. That's typically the operate angle for the line. So a line is typically more inductive. So we usually set this operate angle anywhere between 75 and 85 degrees for this maximum torque angle. So any current impedance that happens to fall within the circle will be in the operate region. Anything falls away from that will be in the non-operate region. Yes? Oh, the question came up, what do we mean by the relay reach? A very good question. If we take the relay reach is the amount of impedance between the points of the relay and how many ohms you want to look out onto the system. Which, for instance, if I have a transmission line that's a 10 ohm transmission line, and I want the relay to see 80% to measure a fault up to 80% on that line, then I would set the relay reach on that of 8 ohms, which means anywhere between 0 ohms and 8 ohms line length, if I have a fault anywhere along that line in that area, the relay will operate for that. That's what we call the reach. And that's the boundary beyond which the relay won't see a fault any longer. That's what we mean by reach. The next the kind of relay that we're going to talk about is called a differential relay. Differential relay can be used for bus protection. It could be used for transformer protection. It could be used for generator protection. It could be used for transformer protection. So there's lots of different ways we can use a differential relay. And it's unit protection, which means we only protect between where the current transformer is located. It's very simple Kirchhoff's law, where we look at the current going into the object and the current going out of the object, and we arrange the CTs so that they're opposite each other, so that the current going through the operate winding is for a through fault current. The current going through the relay will be a net of 0, because the input current and output current would be the same. Where if there's an internal fault, then the current going through the input and out don't add up to 0, but add up some large quantity, and the relay operates. So it's a very, very simple principle based on the fact that that current has to go somewhere, and for through faults, it's a through current where the currents going through both our CTs are the same, and if for an internal fault, the currents aren't the same, and the difference goes in the operating circuit. So we can use the same kind of principle for protecting generators, motors, transformers, transmission lines, buses, and shunt reactors. Looking at a bus type differential protection, here we have a transmission bus with 6 breakers on it, and we just connect all the CTs together on one side and then the other side together, and then sum them up at the relay location. And so any through current coming here is going to appear on both sides of the operate winding. We get no current in the operate winding itself, but any fault that we have on the bus will be current through one side and not the other side, and it will appear as a large operating current within the relay itself. Again, bus differential protection just measures the current going in and going out and sums them together to see if there's any difference or not. Another way of doing the protection for this is called a restricted earth fault protection relay. In this particular case, we take the 3-phase currents coming into this auto transformer or into this transformer, add them up together, and then compare that current against the neutral current in the transformer. By doing this on this wide winding, under normal conditions, if there's no fault in the winding at all, then the summation of the 3 currents in the coming phase currents would be a 3I0 current. That would be exactly the same current that's flowing in the neutral, 3I0. So these two would be matched up exactly the same. Whenever there's a fault internally in the transformer, then this 3I0 doesn't add up to the IN, and the relay operates as an internal fault. This is called restricted earth fault protection. Another type of differential principle just sums up all the currents coming in out of all the feeders into a coil, and we compare the differential current is just the sum of all the currents of each of the different circuits. So ID is equal to I1 plus I2 plus I3 plus I4, and then so this is our operate current, and then we compare that against the restraint current that could be the highest of any one of these 3 currents right here for our operating current. Another way to do differential protection is called a high impedance bus differential relay, and in this case, instead of taking all the currents and adding them together like we see here, we take the currents of all the CTs and we parallel all of them together, and we parallel them all through a resistor and a varistor. All the CTs in this particular scheme have to be exactly the same ratio and exactly the same characteristics, and we actually set the relay by setting the resistance value and the MOV level, operate level, to the porous CT knee point voltage that we have. So this kind of relay is similar to our KAB relay and the GEPVD relay, and the same as they're using modern microprocessor-based high impedance bus differential protections also. The partial percentage differential relay is shown next. Here, where it's similar to what you saw in this particular case, where instead of using overcurrent relay for this example, we're taking the CTs and putting them all into a separate restraint within the relay, and then we're taking the current for an operate quantity. We add up all those currents together for all the different coming into the relay. And then we use a restraining quantity, and the restraining quantity happens to be the largest if any one of our phase currents on any of the widenings. So we actually have a operating curve that says any current time the operate current is up in this area above this line that's operate. Anything that's time it's below this line, it's a restraint. And we can operate, and you can see that this curve has three different regions on it: a minimum operate level, and then a slight slope to it, and then a higher slope. This is so that as the current goes up in the restraint winding, it takes more operate current to operate the relay. And this is basically because as the current goes through a CT goes higher and higher, the performance in a given set of CTs is not going to be quite the same, and this slope is to get by the poor performance of the current transformers. Another kind of restraint, another kind of differential that's come into play recently now is called a negative sequence element. And negative sequence element differential relay actually looks at the negative sequence current on two different parts of the object and compares them together, just as the phase currents we did previously. And then if the currents are in phase, because we know that for a fault, the negative sequence current emanates from the point of the fault. So if we have an external fault, we have a through negative sequence current, and if we have an internal fault, we have a current in two CTs that are opposite each other, and we get this kind of operating characteristic for the relay. So it's very, very sensitive relay, whereas you have to set the minimum operate level on the normal percentage differential relay, normally around 30% of the normal load current. You can set the minimum operate level on the negative sequence differential current in the level of about 4% of the load current. So it's much more sensitive than the other relay was. Next, we have our favorite line current differential relay. This takes the same differential principle that we used for our unit protection, for transfer protection or bus protection, and just expand it so that now this covers the entire transmission line instead. So rather than having one relay located somewhere between the two lines, we have two relays that are separated by some distance, which happens to be the distance of the transmission line. For this relay to operate properly, you need to also have a pilot channel. You have to have a method of getting information from one end of the line to the other end of the line. In the olden days, this pilot channel used to be a pilot wire that was a twisted pair of like 16-gauge wire between one end of the line and the other end of the line that would measure the voltage at both ends of the line for this HCB relay. Another question came up?
What's the bus protection scheme and the relay differential between a fault and switching?
A question came up that said in a bus differential relay scheme, how does the relay differentiate between a fault and switching? I guess I don't quite understand the question, but any kind of a through fault that you would have would not, any kind of switching that you would have would not be seen, would be seen as a absence of current, so you wouldn't get an operation at all. It would be both ends of both CTs would see this lower current, so they wouldn't operate at all. any internal fault that you would have, you would see a definite difference between the current and the two CTs, and it would operate the differential element. But in a switching condition, the current between the two different ends wouldn't change it. It would both go to zero, and so you wouldn't see any differential currents at all. Now back to our line differential relay again. So now in modern line differential relays, now this pilot channel is now a fiber instead, and we used a fiber between two ends of a line, and we send sample data between one end of the line and the other end of the line. But the principle is exactly the same. For internal fault conditions, the CDs are set so that the local signal, which is the signal that we generated locally, and the remote signal that we generated we got from the other end of the line for an internal fault, they add up together, and we get a large differential current. Whereas if we have an external fault, the local current and the remote current are out of phase with each other, and we get so the summation is nearly zero, and so it really doesn't operate. So it's the very same principle, just now we have to use some intelligence to send the current from one end line to the other end of the line to do this differential comparison. The next step in the process is called the directional comparison type relay systems. Here we have to use a pilot channel again, and we want 100% clearing for the entire length of line. When we use a normal distance relay, as we said before, I mentioned, we only typically set that distance relay to 80% of the line length. So that leaves 20% of the line that's going to not be protected by our zone 1 relay. It'll be protected by another relay, but that'll be set with a time delay so that it will trip in like 30 cycles rather than instantaneously. The reason for this is we never want to overtrip the relay and trip for a fault external to the relay or on the bus. So we can do some things instead. We can set a element that looks past the far end of the line from one end of the line, and then we can set another relay looking from the remote end of the line back toward the other end line through it also. And this could be a permissive scheme, so that if I'm sitting here and I see a fault all the way through, I see a fault on the line, and my other end of the line also sees a fault on the line going the other direction, it sends a permissive signal to my end that lets me trip. So there's permissive overreaching schemes where we overreach the other end of the line, and there's underreaching schemes where we reach under the other end of the line. We don't reach the other end of the line, just a short, like our 80% setting before. And again, we have to, but the permissive scheme, you need to receive permission from the remote end to trip. There's also a blocking scheme. In the blocking scheme, we send a signal from to the remote end of the line if we see a fault external, which in this particular case at this terminal, we have a relay that's reaching backwards, reaching back toward the other end of the line, the other direction. When it sees a fault within that zone going in reverse direction, it sends a blocking signal to the remote terminal, not the trip. And the remote, conversely, the remote terminal is looking back the other direction too, and if it sees a fault in the reverse direction, it sends a signal to the local end, not the trip. So this is a unblocking scheme, and so that the relay will look forward. We have a forward-looking element that's looking over past the other end of the line, and a reverse-looking element looking the other direction. So if the forward element picks up and the reverse element doesn't pick up, then it sees it's a legitimate fault and trips. And then there's also a blocking scheme also. Blocking scheme and the permissive overreaching scheme are the same, but a blocking scheme typically is used with a power line carrier system where there's a possibility that during a fault, we're using a power line for the communications channel, and if I have a fault during the I have a fault and I lose my communication signal, I have a 150 millisecond window of tripping while that signal is lost if my local relay sees a fault in the forward direction. So that's what the unlocking scheme does, how it's different from the POTT. So those are the different kinds of schemes you can use with a directional relays, either overcurrent directional relays or impedance directional relays. Another part of the scheme is called an internal schematic, and this just shows what the internal schematic looks like for a typical. This happens to be internal schematic for a overcurrent relay, or a steel relay with 2 elements. So this shows you that it shows you the terminals on the back of the relay. It shows you where you hook up the overcurrent element to between terminals 9 and 10. It shows you where the output goes between terminals 1 and 10, how you would wire this up together. And then it has other elements, the instantaneous element, and then the ICS unit also. We relate that to the AC external schematic, where now we have current. We show that our station 1 line diagram showing our phases, line 3 phases, and we also show on there how the relay is connected to that, how the CTs are connected to that, and then the CT inputs coming into the different terminals on the back of the relay. And you see this is for 3 different relays: phase A, phase B, phase C, and the neutral relay, connected between terminals 9 and 8, like we said before. So this shows you the AC schematic about how the CTs and the relays are connected to the AC scheme. Then there's a DC schematic that takes the output of the relay, and that's between 1 and 10, as we said before, and then that connects in through the 52A contact into the trip coil of the breaker, again for each of the 3 phases in ground. And then in numerical relays, now we have to go one step further, and we have logic that you can apply to the relays also, or you can put in the relay, and this shows you a diagram of some of the logic that you could have in the relay. And again, all 3 of these pieces of schematics, the AC schematic, the DC schematic, and the logic diagram, all go together to show the operator how the relay performance how it should be hooked up and how it should work. We said before that IEEE device numbers are part of our whole nomenclature. We have ways of representing any device, whether it be a impedance relay or a overcurrent relay or a auxiliary switch, all by certain terminology, so it's easier for us to write things down rather than writing it all out on a drawing. Another question came up. The question is, are these protection schemes only applicable when using pilot? Yeah, pilot. Yes, these schemes are all pilot. Pilot protection means I'm using a communication scheme to talk between one end of the line and the other end of the line. And yes, all these permissive overreaching and permissive underreaching schemes that we talked about are all schemes that are used with pilot protection, so that we get 100% clearing for the whole line for any internal fault. That's right. So back on IEEE device numbers. So IEEE has come up with a way over the years, actually this goes back into the 1930s, of identifying, assigning names to different types of devices so that we can write the device name number down rather than write the whole device down. So if you look at IEEE C37.2, that's 1991. Actually, it's been updated to 2010 now for the IEEE device numbers. You'll see a whole listing of the definitions for relays and also for the numbers associated with those for different processes. Some of which are that you can see on this page. Where we have a 58 unit is a high step instantaneous element. 50 is an instantaneous overcurrent relay. A 21 relay is a impedance relay. So here we have zone 1, zone 2, and zone 3 for 3 impedance relays. In zone 4 of an impedance relay. 21N is these are phase impedance, and 21N is a impedance ground distance relay for 3 zones of that, phase 1, zone 1, zone 2, zone 3, and zone 4 of the ground distance relay. 67N, 67 means a directional relay, N means a ground relay, so it's a directional ground relay for 67N. Then 62 relay happens to be, these are all timers. So associated with zone, usually with zone 2, zone 3, and zone 2 and zone 3, we have a timer associated with them so they don't operate instantaneously for coordination purposes. So here we see the that all each of those defined. Then we also have other terms we define as SCR for sequence of events recorder, DFR, our digital fault recorder. All these are different types of relays, different types of parts of the system. And this shows you the current transformer inputs. And there's also another device called that we define now called the 11, device number 11. And device number 11 happens to be a multifunction relay. So all of these devices that you see here, the 21s and the 50s and the 21Ns and 67s and the 62s are all involved in this, all part of this 11 device. This is how you can represent those. We also have another way to represent that device 11 device is by showing the different parts of the scheme. 85 happens to be a pilot scheme. This happens to be a permissive overreaching transfer trip scheme. 21 P and N is 21 phase and ground element. 67 is the, as I said before, the directional ground element. SOFT, switch onto fault. 50 BF is a breaker failure relay. And so all these terms are defined in this standard. Then the manufacturers can take these terms and embellish them a little bit by putting their other terminology on those also. Then we have IREG-B, another term is defined now. When they went and went to review and to update this standard, they wanted to add some new device numbers. So they went back and in the old device numbers, and they found some old ones dealing with DC railroads and whatnot, and they wanted to get rid of them, so they sent a note out to the industry about the review group about getting rid of these. And they got a reply back from the old railroad engineers saying, no, don't take those away because those are still being used by us now. So these terms, these device numbers are still being used today for all industries, not just Electric Power Systems Group. Excuse me. And then there's also the last thing we talk about now is the symbols. We want to have symbols to represent different things, whether it be a breaker, whether it be a open or normally closed contact, whether it be a transformer, 2-winding transformer, 3-winding transformer, and how we indicate what the phase is, whether it be a delta or grounded wide transformer. What you see here is just a comparison of the symbols between the IEEE symbols that we use in France and North America versus the symbols that are used by the IEC over in Europe and the IEC countries. So you can see in some cases that it's kind of confusing. Well, we have for a breaker in the IEEE world, we use a square box for a breaker. In the IEC world, they just use an X through a line. But you'll notice that if you look over to the further right for a fault, we use that same X through the line to describe a fault in the IEEE world, but the IEC world uses a jiggly line going with an arrow at the end of it. So the caveat is to be sure that if you're looking at drawings from different people, make sure you know what they're using for a standard, whether it be the IEC standard, the IEEE standard, for any one of these different symbols. Some of them are a little bit easier, like the transformer, two-winding transformer. For us, we have a series of windings back to back. Where in the IEC world, they just use two conjoined concentric circles. A three-winding transformer, we use three sets of windings to show you that. And in the IEC world, they just use three symbols and join together. So it gets sometimes it's easier to use the IEC symbology if you can. And then, of course, going over to the phase rotation, phase designations. In this country, lots of different customers use the A, B, C. Some use 1, 2, 3. But most times in the IEC world, they use RSG for phase designation. And use the one, but we use the same for component positive, negative, and zero sequence components, 1, 2, and 0 in both cases. And then for the voltage in the IEC world, they use the U, and the voltage for the IEEE world, they use a V. So I think that brings us to the end of our first seminar. We're going to be getting this webinar is brought to you by our commercial rail line product family, next generation of protection and control for IEDs from ABB, which are pictured below. In future webinars, we'll be talking more about these products and about distance protection, bus protection, line differential protection, and transfer protection in the future. And also we'll have some seminars dealing specifically with IEC 67850 standard and how it applies to line protection and control circuits. Thank you for participating. As it says, shortly you'll receive a link to an archive of this presentation so you can view it or have others view it. You're invited to look at our website, www.abb.com/reliant, for more information about our